Let's make sure that you guys have this. First thing you want to do is kind of mentally, hey guys, listen up please. First thing you want to do is kind of mentally think about how this limit is going to go. And so kind of that mental approach of like, hey, let's just plug this in and see what happens. Obviously, if you directly substitute in the top, you get integral from pi to pi, which is automatically going to lead you to 0. And then in the denominator, you see pi minus pi, again, heading towards 0. But instead of writing like equals 0 over 0, like we've talked about, we don't want to do that. Or instead of maybe even using the arrows, which again, less offensive, but maybe this would be better. What we'd maybe want to do is write the limit of the top equals 0, and the limit of the denominator equals 0. And this would be considered the optimum way of expressing this. And so by doing so, we have demonstrated that L'Hopital's rule conditions have been met. And we can go ahead and use L'Hopital's rule. So as I try to do that here, what's going to happen in the numerator? Yeah, and what principle are we using to do that like super quick?
FTC2?
That's right, FTC2, derivative of an integral of an accumulation function. You derive and drop, essentially, is what we call that. So you'd get cosine of x. Down here you'd get 1. And because of that 1, you automatically know this is going to end now, right? Because there's no way you're going to get a 0 for a denominator, which would be a condition for another L'Hopital's rule. So now as we evaluate this, we think, all right, well, as x approaches pi, cosine will be approaching -1. Yep, so we end up with equals -1. Therefore, the original limit is also equal to -1. Question?
So if the numerator and denominator were flipped, and it was like 1 over 0, would you just say limit doesn't exist?
How would 1 over 0?
Or sorry, 0 over 1. Yeah.
So
no,
if it was like a little different,
if it just flipped, like if it was like the integral of x to pi of cosine t dt, and that was on the denominator instead of the numerator, and we went through L'Hopital's rule and everything.
and you ended up with like a 1 over 0,
Yeah.
then we'd say limit doesn't exist.
Okay.
Yeah. At some point you might get to that and be like, hey, there must be some vertical asymptote and it's diverging, going in two different directions on the graph, something like that.
Okay. And like if it had like the integral thing, like where it's x to pi, x through pi, and like inside was like x squared minus 2 or something like that, and could we like could we do one part of L'Hopital's rule and then cross out and find the vertical asymptote, or does that not work?
So you're asking if you could simplify the results, like cancel something out?
Yeah, like can you do part way of L'Hopital's rule and then find like a vertical asymptote if the limit doesn't exist?
Part way.
Like, yeah, if you want to continue and I can like make something.
Yeah, show me what you're talking about. Yeah, there might be a good answer to it. Show me what you're talking about. Yeah. Okay, example number 5. Okay, as you look at example number 5, again, hopefully you'd look at this and mentally do some direct substituting. If you did plug in the 1, you'd end up with 1 minus 2 plus 1, and so the limit of the top heads towards 0. And then you'd do the same sort of thing with the denominator. And you'd say the limit as x approaches 1 of cosine of pi over 2x. And by the way, definitely a no calculator sort of a question. You got to know the unit circle, right? Cosine of pi over 2 is 0. So the conditions for L'Hopital's rule have been met. Limit of the bottom and the top are both 0. So we try L'Hopital's rule here. And in doing so, I would get the limit as x approaches 1 of 3x squared minus 4x, all divided by negative pi over 2 times sine of pi over 2x, using that chain rule in there. So now yes sir? How do I what? Oh. I don't know. I think sometimes, so this has palm reject, like the Apple Pencil has palm reject. So like if you don't have this, if you put your palm on the screen, it'll like try to take that as an input. And so I can put my hand on here, but the palm reject is not quite perfect, so sometimes I'll put my hand on there, and it'll like get a little confused, and it just won't write anything. So I'm guessing that's what happened, or maybe I just forgot. I'm not for sure. Okay, so as we try this, you can see the numerator is not going to be 0, so no more L'Hopital's rule. So this is going to equal negative 1 over, and then I guess it's just negative pi over 2, right? So we end up with 2 over pi for a final limit. Therefore, that would be equal to the original limit as well. So, guys, I want to make sure that the points of emphasis have been emphasized. To use L'Hopital's rule, you must show that the conditions were actually met, and that is the preferred, aka probably required way of doing it. Changes from year to year a little bit how much of a stickler they want to be about this stuff. And then you apply L'Hopital's rule, hopefully once, maybe twice. If you've got to do it twice, you've got to show the conditions were met again. And then hopefully you're good. You guys have any follow-up questions, anything you need to talk about with this stuff? All right, fair enough. So then we are going to do something I am super pumped about. We're going to do this is the final section in Chapter 8, and we'll spend a couple of days on this. And this section is called Improper Integrals. And this is going to be really fun. This is going to lead us to some cool places. And of course, I'm sure you understand improper integrals are not like integrals that are rude, like don't know how to talk to people, and they're just sort of like improper in their dealings with folks. Improper means that there's something wrong with all of these, and we have to deal with a workaround to make these work. So you may or may not remember this. It's been a long time, and I didn't make a really big deal about it. But in order for us to be able to evaluate a definite integral, the integral has to be continuous on the interval that we're dealing with. And so an improper integral is a definite integral where the two limits, one or both of the limits, is infinite. And so when I say that, I am talking about something like this. What if we had the integral from 2 to infinity of f of x dx? So that's where one of the limits is infinite. So you start at 2 and you accumulate all the way towards infinity. In other words, you really don't stop accumulating, right? Keeps on going forever and ever. Or if you have a definite integral that has a finite number of infinite discontinuities, something like this. What if I had the integral from 1 to 5 and the integrand was 1 over x minus 2 dx? You see how that integrand, if we graphed it, it would have an infinite discontinuity within that domain. What kind of a discontinuity would it have? 1 over x minus 2. Isn't that a vertical asymptote at 2? Not a whole, because there's nothing to cancel out there. That's a vertical asymptote there at 2. And you think, really honestly, what this graph looks like, I'll draw a few more graphs here in a second, but you'd have this vertical asymptote at 2, and I think it would do this and this. And you think, what if we were integrating from 1 out there to like 5 somewhere? How is that all going to work out? And it's really tempting to just be like, oh, they'd all be infinite, right? Because there's a vertical asymptote, or there's, one or both of the limits are infinity. And you're going to find out that sometimes the answer is infinity. And we'll have a special word for that. Other times it's going to be a real number. It's not going to be infinity or something we can't figure out. We'll talk about that, the patterns that emerge from that. Okay. So an improper integral allows us to find the area under a curve for an infinite domain, range, or both. Because of the fact that these are improper integrals and you're going to have infinity in here somewhere in some shape or form, we are going to have to use limits. So like actually writing LIM with x approaching whatever is going to be pretty important here. And I mentioned a second ago, sometimes you're going to get an answer like 7 or 3 or whatever. Other times you're going to get a non-real answer. And the word we'll often use here is the word diverge. So if you get integral from whatever to whatever of f of x dx, and you think, you know what, this thing is heading towards infinity, we probably would just say that that integral diverges, or you could say that, you really don't have to, but we'll start to use that terminology a little bit as we head into the second semester. We'll use it a lot. Okay, so just some examples of graphs, again, of what you could have. What if we had, again, I'll just try to formalize this. I'll put it in a different spot. What if we had some graph, maybe like this. I'll do it a little bit different. This would be a graph that you could for sure see. Anybody have any idea what the equation for that graph might be? Maybe the simplest possible equation?
The absolute value of 1 over x minus 3.
Could be. Can we do it without absolute values? I think your response is pretty reasonable. Absolute value is one way to make all things that used to be negative positive, right?
Weird.
Or you could take an even exponent, right? So I was going with this, Josh, but I mean, I have no reason to say that yours would be wrong. Yours could be right. I don't know. I was going with that. We could go with yours too. So believe it or not, if I did, I don't know, if I did the integral from, let's say, 3 to 5, integral from 3 to 5 of g of x dx. So what we're basically talking about is this purple area. That seem reasonable? You would find, believe it or not, that you get a real number. Right. You think to yourself, well, isn't all the area just going to continue to leak out the top of that thing? Right? Because, I mean, how could you get close enough to the 3? The concept is a limit. We've got to understand that we're going to say it's a limit is going to be the way we calculate this. But even still, you'd think, no way. There's no way that could be a real number. You would find out that it actually is. Depending on the pattern, you'll find, again, sometimes you get real number answers. Other times you're going to be like, yeah, the answer is infinite. So the area or the integral would diverge. Okay. Another example would be something like this. And we'll look at one like this today, Lord willing. What if you had some graph where you have a pretty clear horizontal asymptote? It's supposed to be symmetrical. I tried. But you got a pretty obvious horizontal asymptote right there on the x-axis, right? That make sense? So in the past, we maybe would have done something like this. The limit as x, sorry, I'm getting way ahead of myself. We might have done integral from like -2 to 2. Let's say this is a graph of f of x or something. We might have done this in the past, and if we knew the function, it'd be relatively easy to figure this out. But now what we're going to do is we're going to do the integral from like -infinity to infinity of f of x dx. And we're going to say, you know what? We don't want to find just a little chunk of the area. We want to decide, is there any way we could figure out all of this purple area extending forever and ever and ever to the left and the right? The key idea here is you have to use a limit to be able to calculate this, because the truth is, you never would stop accumulating area. We'd be looking for the pattern that the limit would help us quantify. Bless you. That makes sense? Bless you again.
God bless you.
Are you allergic to purple? Is that what it is? No, maybe not. Okay. Okay, so do you guys have the basic idea of what it is we're going to be doing? I understand there's a lot of details left, and you might be like, well, I don't know how we're going to do that. Are you okay with the basic idea?
Yes.
Okay. So let's do a couple of these. I do have your quizzes done. We'll go over those at the end. But I wanted to make sure we got into some of this good stuff. So we're going to do, I think we'll do 3 examples today. Here is the first one right here. Integral from 1 to infinity of 1 over x squared. And this is kind of like that graph that I just showed you. Josh was thinking maybe it was absolute values. We decided maybe it was something squared. If you want, take a second and graph this on your calculator. I'll sketch a graph up there and kind of see what this looks like, and we'll decide how we'll deal with it.
Did you finish your class? Are you working with a partner?
Oh yeah, for sure. Yeah, absolutely. I just figured I'd text them to you so you could either have them on if you needed to. Yay! On the left side. I thought it was like so and I literally talked to them. It was just my friend who got But if you wanted to, it's like a. Oh, the Cambodia.
Hey guys, graph-wise, are you okay with my representation up there? Okay. So I've taken it one step further, and I went ahead and put that lower limit of integration, which is 1, and I've tried to illustrate the area that would correspond with this definite integral. Does that also make sense? Can you also see why this is a bit of a conundrum? Because you see how, as we think, I mean, the left edge is pretty clear. It starts at 1. But the right edge just kind of keeps on going and going and going, as you know the behavior of a horizontal asymptote long term, as you get closer and closer and closer to the x-axis, but we never actually touch or cross the x-axis, right? So how could this be anything other than infinity? We'll find out. Maybe it is. Maybe it isn't. So, guys, here are your, I want to model some very clear steps for you. And so in order for an integral to be a proper integral, there can't be anything having to do with not existing, like whether that be asymptotes or infinite discontinuities or infinite limits here. And so we've got to work around that. Here's how we do it. My first step really ought to be this. The limit as b approaches infinity of the integral from 1 to b of 1 over x squared dx. This might seem like a little minor step here because we're so used to just limits behaving in a certain way. I've just translated this improper integral into a proper integral with a limit making one of the integral's limits go to infinity, go towards infinity. So you've got to have that step. So I'm going to put a little star by that. If you don't use limits with an improper integral, then it could be said that you don't really understand one of the conditions for an actual definite integral. Okay? So the good news is, because we can use that limit, we know the limit is like going to get closer and closer and closer towards infinity. I can now just go ahead and do like a regular old FTC1 process with the integral. So I'm going to say the limit as b goes towards infinity. And, maybe I do this. Maybe you already did this. Flip that up just so it's a little bit of an easier form. And then we find our antiderivative. So now it's going to be the limit as b heads towards infinity of negative x to the negative 1, evaluated from 1 to b. This is where different variables have very different meanings. The b's and the x's are not the same. And so you want the limit as b heads towards infinity of negative x to the negative 1, evaluated from 1 to b. Right? Let's not get those mixed up. So then we do FTC1. So we continue to have this limit here. And with FTC1, we're going to plug in the b and the 1 and find the difference. So this would be the negative of b to the negative 1 minus the negative of 1 to the negative 1. So, of course, that's really plus a positive. Oops. Like so. And we can kind of finish this one up here. So the limit as b goes towards infinity, it would be maybe negative 1 over b plus 1. You guys okay with that? Flipping that b to negative 1 down. And now is when we can actually evaluate this. If you have a constant over b, and b is getting gigantic, then that first term is heading towards 0, right? That makes sense?
Yeah.
So as you apply the limit, you get 0 plus 1. Of course, that's just 1. So you think to yourself, what? I thought for sure this would give me an infinite value. Infinity, right? It makes sense. Remember what the limit is doing. The limit is not saying, hey, we stopped counting little areas as we accumulated. The limit is basically saying, I see where this is headed, I see the pattern, and here's the pattern for this infinite sum. The pattern is headed towards 1. It makes sense. Yeah, Brandon.
For the first part, when you have, like, the very first step, when you have limit b goes to infinity of the integral, why don't you do FTC2 and just, like, put the b where the x, because, like...
Because we're not looking for the rate of change of anything.
Oh, I see.
If I was looking for like the rate of change of that accumulation function, blah, 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 then maybe I would do that. I agree. But I don't really care about that, so I'm not going to do it.
Okay.
Yep. Curious result, right? Will you guys please try number 2? You have all the tools in your toolbox to attempt number 2. Please try number 2. You can't really rely on your calculators to do all these sorts of questions either. Sometimes your calculator will spit out the right answer. Other times you'll confuse your calculator, depending on the setup and such. So anyway, please try number 2. Biting, man, that's pretty awful.
And he locks himself in the bathroom. As soon as he comes out, the 6-year-old just chops him. I'm like, what am I supposed to do with this? I just...
Hey guys, I'm going to sketch out a graph real quick. Would you guys agree that this graph, at least for the part that we care about, looks pretty similar to the last one? I mean, other than, like, obviously on the last one, the left half was up the second quadrant. This time it's down in the third. But the part we care about over here, and it's really hard to tell the difference between the graph we just did and this one, right? Oops, are you guys getting any kind of a different result? Should be. So we're looking for this area. And really, honestly, if you look, it looks the same as the other one, doesn't it? At least the part we care about. So maybe you did this. Limit as b heads towards infinity. Also looks the same. Integral from 1 to b. And then maybe you did this real quick because you know what's coming next. X to the negative 1. So again, that limit as b heads towards infinity has to be there. You cannot deal with this unless you think of it as a limit. Okay? So then... if you did write x to the negative 1, maybe that was the first thing you discovered. You're like, whoa, this doesn't work. Maybe I should go back and rethink this. And that's where you get the natural log, right? Okay, so it'd be limit as b heads towards infinity of natural log of absolute value of x evaluated from 1 to b. Looking around, I'm seeing people that are like, yep, I had that. Okay, so then limit as b heads towards infinity. Okay, let's just start over. There we go. And it would be natural log of b minus natural log of 1. At this point, I can get rid of the absolute values there because I know that b is for sure positive, and I obviously know that 1 is positive, so I can get rid of those. So I know that ln of 1, I know what that is, right? What's ln of 1? 0. So this comes down to limit as b heads towards infinity of natural log of b minus 0. But natural log of b is the thing I care about the most. So this is where I mentioned if you think about the graph of natural log, this might be really, really helpful. So I'll just sketch this out. This is obviously a different graph than the one I just did. This is natural log of b. Doesn't it look like this? It goes through there at 1, 0. And the important thing is, as x gets bigger and bigger and bigger, doesn't natural log of b continue to get bigger and bigger?
Yeah.
It does it at a slowing rate. Right, it's getting flatter and flatter and flatter, the graph is, but it does continue to go up. So as b heads towards infinity, ln of b is heading towards what?
Infinity.
Infinity, yeah. So we could then maybe write infinity right here, or you could put diverges. That's that new terminology that we're going to use for something like that sometimes. So then this is a little puzzling, isn't it? Because the first one we did, we got 1, obviously a real number. This one, we didn't. We got a diverging answer. We got infinity. So not a real number. There is no, like the area here is infinite. So what's the difference? I'm just going to give you some really informal thoughts on this right now. and we'll formalize this a lot more as we finish out the first semester, and then we'll formalize this a lot more as we go through the second semester. Basically, it's this. Whether that area is finite or infinite depends on how fast the graph is approaching the x-axis. When you think about that other one, 1 over x squared, think about like just maybe plot some points in your brain as x gets bigger and bigger for 1 over x squared. Like if x was like 2, 3, 4, 5. If it was 1 over x squared, wouldn't it be 1/4, 1/9, 1/16, 1/25? But if your integrand is 1 over x, the numbers would be bigger, wouldn't they? They'd be 1/2, 1/3, 1/4, 1/5, 1/6. And so 1 over x squared, because it's squared versus to the first, like in this one, that graph we did number 1 will actually approach the x-axis fast enough, where you actually get a finite area for an answer to these. Where this one is a little bit too slow. Okay, so we'll start to like classify these and understand the patterns a little bit better as we go throughout this section and second semester as well. What I wanted to do here to finish this off is I wanted to do what I'm like super pumped to do number 3. So let's do number 3. We're not going to need that much time for you to go over your quizzes because they're all pretty good. But I want to do number 3. I want to do number 3 kind of with you and hear what you guys have to say about this one. So first of all, for number 3, would you guys just real quick on your calculator graph it? Graph f of x equals 1 over x squared plus 1. You're going to need your calculator for a couple of pieces of this.
I really would like it.
And I'm going to roll with my graphs today. That one actually looks decent. The other ones are okay too. It's a little lopsided now that I look at it. Oh well, I'm leaving it. It's about the best I can do. Did you guys get something similar looking at that? Like a nice round hill? So pumped to see what you guys think about this. Okay, so it says find the area under the function. That's my graph. Did you guys get something similar?
Yeah.
Okay, find the area under the function. What is so unique about this, of course, is that I didn't really give you any limits. I just said find the area. And so we're talking about all this area, but the hard part is, of course, that there's no left endpoint, there's no right endpoint, because you've got that horizontal asymptote behavior towards the left and the right. This graph just keeps on going and getting closer and closer to the x-axis without actually ever touching it. And so what would you guys guess would be the integral that we would set up to find this area? Yeah, those are going to be your limits on your integral. It's going to be the integral from negative infinity to infinity of f of x, 1 over x squared plus 1 times dx. Bless you. So again, you may or may not know the mechanics of this yet, but does this concept make sense? Like why you would set up that particular integral for that particular area? Okay. What do you have to use in order to evaluate an integral like that? A limit. So I'm going to put it like this, maybe the limit area equals the limit as b heads towards infinity. And then it would be the integral from where to where if I set that limit up? Negative b to b. Negative b to b. Yep. Good job. Still over 1, or still of 1 over x squared plus 1 dx. Again, I know this is new, kind of complicated. So far, so good. Any questions about why I've done what I've done? What have I done? Yes, you might ask that at one point or another here. So we're actually into some sort of familiar territory because now we got to find the antiderivative of 1 over x squared plus 1, and I am hoping that this will be pretty apparent to you. What is it? Arctan. It's arctan, right? We worked with that a lot. This is an arctan. Guys, don't miss this. This is going to be so cool. Limit as b approaches infinity. I'm not just being a teacher, just trying to like hook you in. There is something really unique about this. Evaluate it from negative b to b. Still with me? Liz, you look like you might have a question, possibly?
No, I just realized that I screwed up like half of the quiz.
Sorry. I'll hand those back to you in just a second. All right, here we go. So then we do FTC 1, and we say that this is really, limit as b goes to infinity of arctan of b minus arctan of negative b. And this is where your calculator is going to come in handy again, because in order to evaluate the limit as b heads towards infinity of arctangent of b, it would be really useful to know what the graph of arctangent of b looks like, right? So if you want your calculator in radian mode, please graph separately from that other one. Please graph arctangent of x.
Does it have to do with like even and odd function?
Well, arctan is an odd function. My cool reveal is not necessarily about that, although I want to think about that now, actually. I'm not for sure. There might be a cool connection there.
I was wondering if you knew what. I don't actually know.
So maybe you look at the graph, maybe even like get the table feature out on your calculator and start exploring the table as, and let's just focus on this first one for the moment, right here. As b gets really, really huge, arctangent of b seems to be heading towards what? It's pi over 2.
What?
Remember how that works with an inverse function? Gets reflected over the line y equals x. And since tangent has vertical asymptotes at pi over 2 and negative pi over 2 and so on, then those will become horizontal asymptotes. So this becomes pi over 2. And what about the limit as b heads towards infinity of arctan of negative b? So it's pi over 2 minus negative pi over 2, which of course ends up being exactly... Now you got to stop and think about this for a second. This, to me, is the coolest thing ever, because way back in like 5th grade or whenever, you learned that pi was the relationship between the circumference and the diameter of a circle, right? That's how your teacher presented it, and of course your teacher was right. At no point did your teacher ever say, well, pi is also the area under the curve 1 over x squared plus 1. The teacher clearly was trying to push you towards great things, you know? 3rd grade? Okay, fair enough. So, like, when you think about this, this is, like, stunning. Other than the fact that tangent obviously is connected with circles, a circle never came up in here. Like, there's no mention of any circles or diameters or circumferences or anything like that. It was just this graph of 1 over x squared plus 1, and we're finding the area under it, and how on earth is that equal to pi? Pretty incredible, right? So, have you ever heard somebody say, hey, there's this computer that has calculated pi out to like the 10 millionth digit, and there, of course, there's always some corresponding person that has memorized it out to the 10 millionth digit, which is quite impressive. I don't know the purpose of that, but it's very impressive. Have you ever wondered what the computer's doing? It's certainly not like finding like, you know, ratios of circumferences and diameters of various circles and like averaging it or something like that. It's not doing that. What it's actually doing is you can take this, and this is where this is a little bit of a leap to second semester. You can take a function like 1 over x squared plus 1, and you can represent it with what's called a power series. And a power series is this infinitely long string of terms just added together, right? And all the computer's doing is just adding one more, and then one more. Computers are really good at computing stuff, right? And so if you just keep it, if you just keep adding another term on, you get a better and better approximation for, in this case, it would be for pi. And so that's really all it's doing. It's just running calculation after calculation, adding more and more and more terms onto this power series that we could use to represent that particular integral, and coming up with an approximate answer, more and more accurate as it adds more and more terms. Okay? Anyways, I love that question just because it's so unexpected. Really? Like pi? It's easy just to gloss over, be like, yeah, pi, we've seen it a million times. But really? Like pi? It just like showed up for no good reason, other than that's actually the area. Anyways, hope you guys find that interesting. We're going to do some more of these when I see you guys again next week. But for now, I want to hand back your quizzes to you.